So I always start out with, why is this important? Well, probably for most of you, the most important reason is, number one, t-tests are one of the most common statistical tests used in the literature. Probably even more germane to most of you, it's covered in any statistics course. So to get through stats courses, you're going to have to understand and apply t-tests. And the good news is you can run t-tests in either SPSS, Excel, and even with standard calculators. And what do you need to know? T-tests are used to compare two groups, and that's a very important distinction. There are other types of tests. The next most common test is called ANOVA, or Analysis of Variance. The t-tests in the ANOVA are almost identical, except the ANOVA compares more than two groups. So if you're just comparing two groups, so males to females, or if you have a question like true, false, or anything where there's only two groups to compare, then the t-test is your bet. If you have more than two groups, you cannot use a t-test, because what you're doing is you're increasing your odds or chances of committing what's called a type 1 error. Okay, so we want to try not to do that if we can. That's why the ANOVA was invented. There are three kinds of t-tests. That's also an important distinction. There's a one sample, an independent sample, and a paired. Okay, and I'll show you examples of how to do all three. The other thing that is crucially important in a t-test is that there are some very important assumptions that really must be met for the test to be valid. The first is called normality. In other words, you have a normal distribution, a bell-shaped curve. The other is that you have equal variance, and you'll notice in an independent sample t-test, and this can be a little confusing in SPSS, it's called the Levene's test, and I'll show it to you, but it does the Levene's test first to test for the equality of variance, and then it does the actual t-test. So that's so important that it's just always done. What else do you need to know? Well, in any type of t-test, you always have a dependent variable, and that variable must be continuous. In other words, it's on a scale. It has numbers, and those numbers have meanings, that they're not just codes for things. So it's typically, interval, ratio, scale, whatever you want to call it, but it has to be one of those types of variables. And in the case of an independent sample t-test, the independent variable must be categorical. So again, if you're comparing weight, which is a continuous dependent variable, and you're comparing males and females, that's a categorical with two levels. That would be an example of a t-test. So to understand a t-test, you need to understand, but it's a test for comparing means, but to really understand how a t-test works, you also need to understand variation. So here's an example of a bell-shaped curve, and it has the mean in that middle bar, and it has the confidence intervals or standard deviations, whichever way you want to apply that, and that's the variation. As you can see, you can have a distribution with the same mean, but a very different variation or a very different distribution, and that can radically or dramatically change the results that you would get on a t-test. So let's do an easy one. I've actually used this example in prior webinars, so I already have my math worked out here, but let's talk about my commute time. I actually have a really horrible commute time. These are actual real numbers. My average commute time is about 75 minutes. Yuck. And most of the time, it takes between 60 and 90 minutes. Okay, so that's the variation in my sample of commute times. So what we're going to do is we can run a t-test. What we're doing is we're testing for the significance. What is the probability that the variation in my sample could be attributed to chance? And that's expressed as a p-value. If you're using SPSS, you'll never find the term p-value. It's going to be called the SIG, S-I-G, or the SIG two-tailed, but it refers to the p-value, or the probability. Typically, that significance is set at 0.05, or less than 5%. Okay, but it also depends on the type of research that you're doing. Sometimes it could be a little bit more, sometimes it could be a little bit less. But typically it's 0.05, and that would be aligned also with a 95% confidence interval. I'll explain how both of those work. So here again is my example, and we're going to calculate the significance. We're basically going to run a t-test on my commute times, okay? And we're going to run this as an independent sample t-test, okay? So we have my normal commute time, okay, and then we have my commute time during rush hour. So the mean goes from 75 minutes up to 105 minutes. And if you look at the confidence intervals, the 90 and the 95, kind of right in the middle there, you notice that basically the confidence intervals do not overlap, okay? And so that would be an example of a t-test where you would reject the null hypothesis. The null hypothesis in this case would be that there's no difference in commute times from normal hours to rush hours. You could actually also run this as a one sample t-test. If let's say 75 was your known sample, and you say, okay, during commute times it takes me 105 minutes. Is that outside of the confidence interval? So you're basically applying the same concept. You're gonna test for, is 105 significantly different than the 75? And again, in this case, you would find that to be true. Here's another example, comparing morning to evening commutes. And you notice that in this case, so it's a pretty small difference. It only went from 75 to 100. But you notice how these two curves overlap. In fact, their confidence intervals overlap. And what that means is there's actually a section of both of those graphs that are the same. Okay? And that means that there is a possibility, a good possibility, in fact, greater than a 5% possibility, that the difference here is just chance. It's just the fact that, normal variation in my commute times caused this difference to occur.